All right, it's 11:15. We'll get started. So welcome to MATSE 202. So if you have any issues, this week is the week to sort them out. So I've already chatted with a couple people in office hours. If you join the office hours Zoom and I'm not there, just sit tight 3 or 4 minutes, 5 minutes. I might be talking to one of my graduate students. I might have had to step out. So you might see a blank screen. If my computer's just sitting there, I might not be on, but when you join Zoom, it sends me an email and I'm usually there watching my email and doing other work. And so just hang tight in Zoom. And if I'm not there in 5 or 7 minutes, shoot me an email. I might've been like, well, stuff came up, let's make an appointment, something like that. So you'll just have to wait for a couple minutes. Sometimes I'm sitting right there ready to go. So take advantage of office hours Zoom. Take advantage of asking questions before or after class. So the homework this week that's due on Friday is pretty easy. You should be able to handle that. I told you can type it out. That's fine for this homework assignment and just submit it on Canvas. And so we're going to practice submitting PDFs on Canvas and scanning stuff in. So you have that all down and ready to go when you take the exam, because the exams again will be on Canvas, but there will be a written part that you have to submit as well. So you want to be good at scanning stuff with your phone, taking pictures, that's fine, that all works, and uploading it on Canvas without an issue. So office hours are posted, and if conditions improve, or if we need to meet face-to-face, we can always do that, but let's try it on Zoom at least to start. Also, homework number 1 is posted, which is due next Friday, because we have a short week, right? We have no lecture on MLK Day on Monday, so we're only going to have lecture on Wednesday and Friday. But by the end of class on Friday, you'll have all the information. By the end of class next Friday, you'll have all the information that you need in order to do the homework. And so you want to be looking at homework number 1, saying, okay, this is the stuff I need to pay attention to. When Hickner covers this, okay, I've got that question. And so use the homeworks to help guide your thinking throughout the week. And I'll post them ahead of time so you'll have them. And that's a really good way to think about what's the most important material for the class, because there's lots of stuff we're going to talk about, but I'm going to give you an exam on what I think are the most important topics. And the most important topics are the things that we'll talk about a lot, that we'll cover. I don't do gotcha questions. I don't ask you about concepts that we haven't covered. I don't make exams incredibly hard that are impossible to do. And so I'm expecting that people, if they focus on the material and focus on the lectures and what I'm asking you, the exam should be just a nice display of what you know. But it's going to take some work to get there. We're going to have to get used to each other, or at least you're going to have to get used to my style, and especially the material in the class, because what is a polymer, is probably brand new to a lot of you. So we're covering new stuff immediately. All right. So the most important thing about polymers, at least to start, is that they're long macromolecules. And we talked a lot about that, right? We talked about aspect ratio. We talked about molecular width right here. How do you figure out how wide a molecule is? We'll talk about the length of the molecule. And you know that if you add up all the atoms and the chemical structure of a molecule, you can get the molecular weight. And I apologize for having bad units here. That's not going to be allowed on homeworks or exams. Remember your units. But molecular weights of this 200 monomer unit of polyethylene in this case, and here's the monomer unit right here for polyethylene. So 200 of those connected, which is N equals 200, gives a molecular weight of 5,600 grams per mole, which is huge. It's bigger than a lot of stuff you've already studied. It's bigger than the things that you talked about in organic chemistry. And polymer molecular weights go up from there. So we're talking about huge molecules with high molecular weight. And I'll show you through this class that number, 5,600 grams per mole, is directly related to N. So we can figure out how many mers or how many monomers are connected together and get that molecular weight. We'll talk about that. And the way you build up a polymer chain in the case of polyethylene is, again, here is ethylene. I'm just going to draw it without the double bonds. This is one molecule of ethylene. And if we connect one molecule of ethylene to a couple more, and we push some arrows, remember a half arrow is one electron. A half arrow from the other molecule is one electron. We get a new covalent bond here. And then these covalent bonds go away. If we keep on and on doing this, we eventually get a chemical structure that looks exactly like this. And we'll draw in the H's just to make sure no one's confused. You're allowed to do skeletal structures if you want. It's really nice if you draw in the hydrogen, so I know that you know what you're doing, but you can write it however you're comfortable writing it. This is another good way to write it. But remember what this parentheses through a covalent bond means. It means there's just one electron in there. And so the other electron for that covalent bond is in the next monomer connected to it. So make sure you can just write this out. Make sure you understand how those arrows are pushed, and make sure you can understand how we go from monomers to polymer chain. Because this is a piece of polymer nomenclature that we're going to use throughout the entire class. This is how polymers are depicted in organic chemistry, so you're going to have to get used to this. Any questions on this? Yes.
On the previous slide, it said something about how, for instance, for specific polymers, those are different mechanics, we would use the actual average of the weights in order to get to the point.
We're going to get to the averages in a second. So far, we're just talking about exact molecules. A chain that is exactly 200 monomer units long has an exact molecular weight of 5,600 grams per mole for polyethylene. We'll get to the distribution, just not quite yet. Good question. Any other questions on this? Yes.
At the ends of the chain, is there a ethylene double bond?
So that is a very good question. We, for now, are going to leave the chain ends undefined. There's other stuff going on the chain ends. You notice that the chain ends are a very small part of this molecule, right? It's only 2 out of 200, so it's 1% of the molecule. And for now, we're just going to leave the chain ends off the page. We will talk about what's on the chain ends later when we get into more advanced concepts and we learn about the chemistry of this, because the chain ends are important in polymers. But for now, we're just going to leave it as, I don't know what's going on out there. So some people put a star right here. I don't suggest that. Some people write this as a dashed bond instead of a solid bond. I don't like that either. What I really like is just, let me undo this so that those notes aren't in there. For now, just leave your polymers like this. Oh, let me erase that. Leave your polymers like this, and if I want to know about N groups, I will ask you about N groups, and then we'll discuss it. Yes?
So I remember seeing a demonstration of like a semi-liquid or a liquid that was like all one chain that pulled itself out of the cup after it was poured. Is that because the end of the chain chemistry is drastically different from the interchain, like the middle segments, or is it still like
So
same chemistry?
yeah, so it's usually in a case like that type of liquid, it's all the same chemistry, and there's just some connections between chains that make it all one molecule. And so we'll talk about cross-linked gels, we'll talk about cross-linked polymers, and formally, since those have bonds between different parts of the chain, they're all one molecule. I mean, it's usually started as a bunch of different molecules that cross-link together and all connect, and it gives that weird behavior, that viscoelastic behavior, right? But we'll get to that. But that's usually just all one type of chemistry. Good questions. People are thinking about polymers. I like it. Any other questions? All right, so make sure you have this. If you don't understand this, you need to study it. You need to ask questions in office hours because this is foundation. All right, so there's lots of polymers around there. There's soft polymers, there's hard polymers, and in a lot of cases, you don't know what the polymer is just by looking at it, right? This is a nice clear polymer. We know it's a contact lens because it looks like a contact lens. It's a soft contact lens because I told you it's soft. And the chemical structure of this soft contact lens is this thing right here. So this cross-linked hydroxyethyl methacrylate. You don't need to know all the nomenclature for that right now. We'll get there. But we know that this is a relatively flexible polymer because it has a carbon-carbon backbone. There's other stuff in there, right? There's R substituents. Here's R1, here's R2. There's no R's, there's H's on this carbon, right? That's the distilled version of the polymer structure. If we just call this thing R1 and this thing R2, but since it's all sigma bonds in the backbone and all sigma bonds between carbons, we know that those sigma bonds can rotate, right? And we're going to talk about rotations and Newman projections and stuff like that. I know you loved it, and you just are going to have to dredge that up. We're going to use a simplified form for polymers. But it's important to recognize that around sigma bonds or single bonds, right, we can rotate those carbons, which means that the substituents here, R1, R2, and these two H's can rotate around. The backbone can rotate around, and that's what gives polymers its flexibility. All right, this is a clear polymer that's also used in eye or ophthalmology. This is polycarbonate, and you see they put dashed bonds here. Let's make those solid because that's just a better way to do that. But you see that this is a lot more complicated polymer. It's clear. It kind of looks like the previous polymer if you just have a piece of it and are looking at it, but it's got a completely different chemical structure. It's got aromatic rings in it. It's got oxygen atoms in it. We call those heteroatoms. And if you remember about electronegativity, which we're going to talk about in a second, this polar. And so that carbonyl introduces polar character. So now you have dipole interactions. These aromatic rings are big compared to just a carbon atom, right? They've got lots of electrons and they move pretty slowly. Big molecules move more slowly, and that makes this a stiff, glassy polymer. So it's a really interesting contrast that you've got polymers that you use in ophthalmology. One is soft for soft contact lenses. One is hard for lightweight eyeglass lenses, and they have completely different chemical structures. And so you don't need to know all the details of this right now, but these are the types of things that we're going to talk about in the class. And so when you see in a few weeks or in a month, a chemical structure that looks like this with lots of aromatic rings in the backbone versus a chemical structure that looks like this with this carbon-carbon bonded backbone, you'll say, ah, I have an idea about what those properties might be. We'll get there.
A quick question about the lens behavior of these.
Yeah.
Are they the lens themselves?
Yes.
Are they housing?
They are the lens themselves. So they fill up with water because you see this thing looks a little hydrophilic. It has that OH on there, right? And so they are the lens. So when you put a contact lens on, that is a teeny little lens that right next to your cornea, and it can be very thin because it's right next to your eye. Lenses are a little bit thicker. They have to be more curved because they're just further away. Yeah, but this is the lens material. Yes.
Explain again real quick why it makes it so stiff compared to the actual lenses.
Yep, so this is stiff. So this one's flexible because carbon-carbon bonds can rotate around sigma bonds. This is stiff because it has polar character. And the aromatic rings are big and rotate slowly. Big molecules move more slowly than small molecules. And so polycarbonate is very stiff, and that makes it hard and glassy. You know, polycarbonate is like plexiglass, right? Although they're different chemical structures, but it's a glassy material. And so you should, in the future, again, when you see stuff like this, it'd be, that's probably a stiff polymer. It's probably glassy. And when you see chemical structures like this, your initial impression is, I get rotation around those carbon-carbon sigma bonds. That's probably a flexible polymer. Other questions? Great. So we encounter a lot of polymers in everyday life. These are the recycling codes for a lot of common polymers. And so why do we have recycling codes on polymer things or plastic things? Does anyone know why? Yes.
Is that because some can actually be like reused on purpose and other stuff to be completely discarded?
That's right. So we have to throw away some plastics because we can't recycle them. And we really want to keep others. But why, in a lot of cases, if you go to a recycling center, there's a bin for plastic 1. There's another bin for plastic 2. There's another bin for plastic 3. Yeah.
Because they need different processes to,
That's right. They need different processes and they don't mix. So if you take polymer 3 or polyvinyl chloride and try and mix it with polymer 1, PET, they don't mix at all. They don't make a good material. You can't make a solid piece of plastic out of that. It's like trying to mix oil and water, even though they're both derived from oil. They've got different molecular characteristics, and you know that like dissolves like, right? Ethanol dissolves in water to make a molecular solution. That's great. But olive oil doesn't dissolve in water because the molecular structure of olive oil is so different from the molecular structure of water. The intermolecular interactions are not strong enough to make a solution out of those molecules. And polymers operate very much the same way. And so there's very fine details and some math that we're going to talk about for polymer mixing. For now, you could say, well, polymers don't mix because they have different chemical structures. And so like doesn't dissolve like in some cases. So I want to highlight the case of low density polyethylene and high density polyethylene. You see here, their chemical structures are exactly the same. And you would say, well, they mix, like dissolves like. However, in order to get low density polyethylene or LDPE, and low density is no secret, it's just lower density. Higher density polyethylene has a higher density. Their chain structure is completely different. So the chain, or this macromolecule for HDPE, is one long line. The monomers are connected perfectly in sequence. You just get a linear polymer. So we call this linear chain structure. And the way, or the reason that low density polyethylene is low density is it has a bunch of branches that don't pack together very well. There's a little bit of space in there. And so things that don't pack well have a lower density. And so we call this a branched chain structure. There's other differences that we'll talk about. The crystallinity is higher in HDPE. They're made a different way because you need a different synthesis technique to get branches versus getting linear polymer. But this is the one extra thing that we have in polymers. We've got the chemical structure, carbons, hydrogens, sticks, bonds, all that stuff, parentheses. But then we have the chain structure as well. So sometimes you don't know the chain structure and you have to assume it. You just say, I assume this is a linear polymer. I'm going to draw it out. Sometimes I'll tell you it's a branch structure and you can tell me about its properties. And so don't forget that between the organic chemistry and the properties, we need to think about what these chains are doing. And so that picture should always be in your head. Okay, it's polymers class. I have a big chain-like molecule. What could that chain-like molecule be doing? Any questions on that? And so we have some shorthand in polymers. I already showed you the shorthand for drawing chemical structures, right? We'll have to get familiar with that and fire up our organic chemistry again. But the other shorthand is, instead of drawing a bunch of different dots connected to each other, or having to draw out all the chemical bonds, we'll just draw the chain like a line, or like a branch line or string or what have you. And so this is just shorthand for what the chain looks like. And all the monomers, again, are in there. We don't know the molecular weight of this thing because I haven't given you any information on that. And so this is just shorthand for representing how the different monomers are connected. Yes.
When would one be preferred to the other? Like, when would you prefer a linear versus a branch?
Depends on the application, right? And so it depends if you want high crystallinity. HDPE, if you make some plastic bottles out of it, it cracks because it's brittle, because it's more crystalline. LDPE is cheaper because it's easier to make and it's a little bit more flexible. And so in some cases, it just depends what properties you want, and then the polymer is tuned to get there. Yeah. Yes.
This might be a loaded question, but like at polyethylene plants, they make the polyethylene, but then what is that process of differentiating between the LDPE and HDPE? Like, how do they make it branch?
Yeah, so you have a petrochemical refinery that, basically makes ethylene from natural gas, most likely, or crude oil back in the day. And so they send part of that ethylene to the HDPE reactor, and they use a very special catalyst called a single site catalyst that allows you to line up those monomers one by one by one by one. So that's the HDPE plant. Then they send the other part of the ethylene to the LDPE reactor that's at high pressure, lots of radicals. Ethylene's flying all over the place and it just branches because of the chemistry. And so it's completely different chemical reactions, catalysts, conditions that make those two different products. And they just decide how much of each to make, depending on what their customers are. We will study some of this catalysis, and you can study it in detail in the advanced polymer classes. But that's, in general, it's just, even though the polymers kind of look the same and start with the same monomer, the process is completely different. Great questions. Anything else people want to say before we move on? Awesome. I'm loving this class already. This is great. Let's see. We talked about old polymers. That's fine. We talked about Dr. Koala, who's a famous polymer scientist from Newquay, PA. That's awesome. And it turns out that there's been lots of prizes awarded, lots of Nobel Prizes awarded for polymer science. And so Staudinger, who is considered the father of polymer science, in 1953, he won the Nobel Prize for just proposing that polymers were chains in the first place. This is after Bakelite. This is after a lot of, celluloid, after a lot of different polymers that people were using. But not until 1953 or a little bit before that did people even hypothesize that these macromolecules existed. And then since 1953, there's been an explosion of polymer science. It's a huge field. There's big meetings about polymers, and also, of course, big problems because we have a lot of plastic and environmental pollution because of it. The most recent Nobel Prizes in polymers were awarded for electrically conducting and semiconducting polymers, and Professor Heeger and Professor Shirakawa are still alive, and so you could go see them at meetings. Professor Heeger's easy to spot with the big bushy beard. He looks like an old professor. And also for single site catalysis, as a matter of fact, not HDPE catalysis, but another special type of catalyst was invented by Bob Grubbs, who's still a professor at Caltech, and Richard Schrock, who's a professor at MIT. If you go to graduate school, you can go work for these people that are still go to meetings. Bob Grubbs' son is a polymer scientist as well. And so you can see them having lunch together. It's really great. And then Professor Chauvin is in France, and he's likely retired to the good life in France. But polymer science is really still being invented today. I mean, we're working on it for additive manufacturing. We're working on sustainable polymers for packaging. We're trying to fix the plastic pollution problem. And so polymer science, the stuff we're going to talk about, is exactly what we study in research labs and exactly what big companies do to try and invent new polymers and come up with new products. So it's a really interesting field, and this is modern stuff that's happening right now. All right, let's see. Okay, just a reminder for you and for me, make sure you have all your material. Don't forget the PLAs. There's one due on Thursday night before you come to class. Remember, the day before every class, go check the PLA, make sure you do it because it turns off at midnight the day before class, right? Because it's called a pre-lecture assignment. And so I don't want to burden you with trying to crank it through in the morning because I know you have stuff to do before this class. So there's a PLA due tomorrow night. Just do it. And if you're on Canvas regularly, you'll see the dates coming up. Get them in your Google Calendar. The PLAs are not going to take long. Half an hour, 45 minutes max. Just do them. And remember, you only need to get 75% credit. And so it shouldn't take you 4 hours to agonize over a PLA. There's tons of PLAs. I think there's 30 or 35 in the class. Just make sure to march through it and use it to guide your study. Okay, don't forget about notes. Don't forget about the syllabus. Let me know if there are issues, and bring your clickers on Monday because I really want to see who's in lecture. All right. Any questions, any comments? All right, we'll switch over to note set 2. We'll bounce around in the note set a little bit. In general, we'll go 1, 2, 3, 4, 5, 6, but things will move back and forth a little bit. There are some repeated notes just as reminders for me. And so when you download the notes and you start using them to study, feel free to delete the stuff that is not going to help you study. Just keep a copy of it as a reference, but it should be all in the syllabus. And so we'll go like that. All right. So I just talked about big companies, and I just talked about polymer science being a really important field, especially in the 1900s and really middle of the century. Plastics are taking off, and one of those people that ushered in the plastic revolution was Dr. Green. So Betty Washington Green got her PhD from a university called Wayne State University. Does anyone know where Wayne State is? I must be the only person from Michigan in here. So it's a big university in Detroit. It's like the Penn State of the Detroit area. So the big universities in Michigan are Michigan State, University of Michigan, and Wayne State is the other big one. And so they have it turns out they have a really awesome chemistry department there because Dow Chemical is just up the road from Detroit. And so even though we've never heard of Wayne State University, they have a great chemistry department where Dr. Green got her PhD. She was also the first Black woman to work for Dow Chemical. That's notable. And what she worked on was these things called latexes. Why can't I draw on this? Oh, draw. Uh-oh, sorry here. I got to sign in. Always. Hopefully I won't type my password in front of class. It's happened before. We'll see how it goes. All right, 2-factor, great. Making sure we're all locked down. Always updating. All right, let's see if this takes here. Well, maybe I won't be able to draw. Who knows? Come on, you can do it. Okay, well, we'll go for it no matter what here. But anyway, she worked on stuff called latexes. And latex is a type of polymer. Who's heard of latex paint? All paints are polymers, right? And so even though it looks like a liquid, it's actually an emulsion of polymer and solvent. And so a big innovation in paints was, how do you use water to disperse that polymer rather than using really nasty VOCs and other stuff like that. And so Dr. Green was one of the people who came up with a lot of the latex formulations and the emulsion formulations for new types of coatings and paints. And you can see some key words here: carboxylic acid, copolymerizing agent, phosphates, and coatings is just a fancy word for paints. There's a big company that does paint in Pennsylvania. What's it called? Come on, Steelers fans. PPG. Yeah, that's right. So Pittsburgh Paint and Glass is mostly now Pittsburgh Paints and Coatings on glass. They don't make any glass. Corning in New York makes the glass, but PPG is a huge paint company, and we send a lot of polymer scientists from Penn State to PPG to go work in Allison Park, where their research facility is. Anyway, this is a cool story, and I just wanted to get across the point that there's lots of opportunities in polymers. And of course, there's a lot of cool things. 3M is a really interesting polymer company. They make all sorts of coatings. People are interested in flexible screens. We finally have foldable phones, right? No matter how dicey they are, but a super flexible phone is coming. We've got organic photovoltaics, and so solar panels that you can bend or you can put on curved roofs. Those are all polymers, and there's just tons of different polymer coatings out there. Any questions or comments on that? All right, so I put some notes in here just to refresh your memory about bonding. I'm not going to go through them all because you should all know this, but in terms of polymers, we're really going to focus on these elements right here: carbon, oxygen, hydrogen, nitrogen. And so make sure that you know all of those organic molecules from organic chemistry. I'm going to tell you exactly the ones you really need to know, but this is where we're going to focus because these other elements are not often used in polymers. So the most important atom that we're going to talk about is carbon. And so you should know a lot about carbon. 4 bonds to carbon, have to complete the octet, sp2, sp3, hybrid orbitals. What is the geometry? Is it trigonal planar? Is it tetrahedral? Those should all be keywords that you're like, oh yeah, I remember that from organic. I might have to go check out a couple of those things tonight to make sure. But this, you want to get all the carbons right in this class for sure. We're not going to talk about too much. We're not going to talk too much about orbitals, but we are going to talk a little bit about molecular geometry. And so I'll have an exercise for you on that. Skip Leonard-Jones. The other important chemistry concept, and I just touched on this when we talked about polycarbonate, is that we have non-polar bonds in polymers. Carbon-carbon bond, right? Same atom bonded together, it's not polar. And then we have polar bonds where the electronegativity is different between the two atoms bonded to each other. Carbon to oxygen, chlorine to carbon, things like that. And so you want to pay attention to where signals of polarity may be, because when you have a non-polar molecule, what's the major intermolecular force between two non-polar molecules? Go ahead, say it. Yeah. Dispersion forces, van der Waals, London forces, whatever they are. Are those strong intermolecular interactions relatively? No, they're weak, right? So if you have two non-polar polymers, they don't stick together very much, or they have weak intermolecular interactions. You better have entanglements and other things to hold them together. When you have polar bonds, or you have two polar molecules, what are the IMFs between those? Or the strongest IMF? Yeah. Well, we can get to ionic, but before we get to ionic, say two covalent molecules interacting. Yes. dipole, right? We have two dipoles interacting, and we know that dipole interactions are stronger than dispersion interactions or London forces or van der Waals. And so that's really important, because if we have polar polymers now, they can have slower chain mobility. That leads to more glassy polymers, higher TG, all the things we'll talk about. So you just want to have that locked down and make sure that you remember that from high school chemistry or first year chemistry. Okay, you can read about electronegativity, that's great. Ionic bonds are not common in polymers, but since we use carboxylic acids, this is a really cool example of ionic bonding. We won't talk too much about this, but you can just look at this example. If anyone's ever done the sodium acrylate adding to calcium salt experiment, where you make, what are those things called? Synthetic caviar, or those little microbeads where you pour the solution in and you make those snakes in solution. You can check out the YouTube video here, and this is the polymer chemistry that's used to do that. It's very interesting. All right, octet rule, you should know all that. This is important. So when you draw out polymer chemical structures, this might seem a little bit elementary, right? But make sure you don't violate the easy stuff when you're trying to do something hard in polymers. Make sure you have 4 bonds to carbon. Make sure you have 3 bonds to nitrogen. Make sure you know where that lone pair is. Make sure you have 2 bonds to oxygen. Make sure you know that oxygen has 2 lone pairs. And this allows us to write stuff like this, where we know that all of the hydrogens are bonded like this, right? We need to obey those rules of bonding. So you'll see a lot of shorthand. Don't forget this. Or you'll see benzene in polymers written like this, or you'll see it written like this, or we put the double bonds in. And one of the critical errors that people forget about benzene is you need 4 bonds to carbon. So sometimes you don't get to see those hydrogens and you get the homework problem wrong because you're not adding those covalent bonds and those hydrogens in there. I shouldn't have to draw them out because I just told you, make sure you have 4 bonds to carbon. And if we don't show something like this, because we're getting to be polymer professionals, you absolutely know that there are hydrogens there. Yes?
So when we are asked to ever write at a log or anything like that, we like to first write out the full structure.
As long as it's correct, I don't care how you write it. And as long as you understand what you're doing, and as long as I can interpret what you're doing, it has to be clear. You know, this is super clear. This is super clear. This is not so clear because I don't know necessarily that you know that there are hydrogens there. However, this is clear. When I draw this line structure, just like I draw benzene, I know that there are hydrogens in there because you're using the nomenclature of organic chemistry that leads me to say, they know that there are hydrogens there. Here, I'm going to put an X through there. Because you've drawn out the atoms and you haven't drawn out all the atoms, I don't know that you know that there are hydrogens in that. So this one's fine. This one's fine. This one's fine. This one's not fine. These are fine. So make sure you develop a way to do this. Test it out on the homework, although we're not going to grade the homework super carefully, but you're going to want to make sure to answer all the questions and do enough work to get the full credit. But you know, really start to work on this. And so you have a shorthand way that you understand, and that's very clear to communicate to me that you know what you're doing. Stuff like this is not good because it's not clear to me that I know what you're doing. Any questions? All right, if you're going to draw the atoms, draw them all out. If you're going to do lines connected, stick with all lines connected. All right, lone pairs, that's fine. this is important. And so we're just drawing on 2D pieces of paper here. You're going to be drawing on 2D pieces of paper when you do the exam and homework. You don't need a molecular modeling kit for this class, although if you have one from organic chemistry, like I do, or if you have a computer program that shows you 3D animations of molecules, they're fun. You know, you're just hanging out on a Saturday night thinking about how molecules are shaped, and go break out your molecular modeling kit. But when we write something like this, especially when carbon's in the center, we know that this is a tetrahedral geometry. That's the technical term, and so that's the one I expect you to use. And the angles between the corners of the tetrahedron are 109.5, or the bond angles in the tetrahedral geometry are 109.5. We know that this is trigonal planar, and we just don't call it planar, we call it trigonal planar because it forms like a triangle, right? And so the bonds in the trigonal planar are 120 degrees to each other. And then of course, 2 points makes a line, and so this molecule is linear because that's all it can do, right? It can only be a line. So just make sure you know how to connect the geometry and what the hybrid orbitals are to that. All right, that's great. We're not going to do a lot of orbital hybridization ourselves, but just make sure you know the difference between sp2 and sp3 carbon. Make sure you get all the lone pairs for the halides, that's fine. And so here's my question on this molecule. Does anyone know what this molecule is called? If you had to take a shot at it, how, you know, knowing some rules of how we name molecules, how would you go about this? Yes. Yes, this is carbon tetrachloride. Carbon is in the center, tetra is 4, and it's got chlorines in it, chloride. That's great. What if I make the molecule like this? Does anyone know what this molecule is? Yes. Why isn't it called carbon tetrahydrogen or something like that, or tetrahydride? Yes. That's right. Meth is a different type of nomenclature because anytime we have meth, it means one methyl group, methane. And so there's different ways to name molecules. There's also IUPAC nomenclature and common nomenclature, and the polymers can have trade names. And so we're going to try and use the most common nomenclature. So this is almost always called carbon tetrachloride. Methane is almost always called methane, and we're just going to have to be flexible with how we discuss the names of the molecules. But I'll try and be precise in terms of how I would like you to answer the question. All right. Okay, so is this bond polar or not polar? Polar. Why is it polar? Yes. Different electronegativities, right? And Cl is more electronegative than carbon. That's right. Is this molecule polar or non-polar? Why is it non-polar? Perfect. So carbon tetrachloride is a non-polar molecule, but it's made up of polar bonds. And we know all that symmetry cancels out. This can happen in polymers. Sometimes it doesn't happen in polymers, but you need to stay up on that stuff and examine it case by case. Great, great job. All right, okay, we have all of that. All right, we're not going to have a clicker question, and so don't worry about it, but these are the type of questions that I'll ask you in class. Anything with a little symbol on it like this means a clicker question. So next week you'll break out your clickers and answer. And so which molecules are polar? And so we can look through here. Okay, no net dipole. I don't know why the answer is here. Net dipole, net dipole, net dipole. And so we can pick out the polar molecules and the non-polar molecules, and we can answer. Great. And so remember, when we have molecules like ethylene that we already talked about, that double bond is composed of one sigma bond and one pi bond. We can also have things like acetylene. So this is acetylene. It's an alkyne, which means there's a triple bond in there, still 4 bonds to carbon. And in order to satisfy all the bonding in carbon, we throw some hydrogens in there because that's probably a good guess. And so in acetylene, there's 1 sigma bond and 2 pi bonds. And we can do exactly the same thing that we did with ethylene. We can sacrifice, I'm going to draw it like this, just for arrow pushing reasons. We can sacrifice an electron from one of those pi bonds, and we can make polyacetylene, just like we made polyethylene, right? If I take 2 electrons from that triple bond and push them out to make bonds to other things, now I have alternating double bonds, because I still have a double bond that's between these carbons, because I only killed one of these, and then I've got a sigma bond on the outside, and we call this polyacetylene. And this is the polymer that Heeger and Shirakawa and McDermott discovered in Philadelphia that they won the Nobel Prize for. Yes. Yes. So if I'm examining you, you probably want to draw the hydrogens on this just to make sure. I'm going quickly, so I won't always be perfect up here. But yeah, it is best to draw the hydrogens. Yes. Good catch. Other questions? I see another hand? No? Okay, cool. So, and again, molecules can be represented different ways. We just talked about this. And so draw out all the atoms and draw out all the bonds, or draw out the sticks, that's fine. Don't mix them. I will try not to mix them, but going fast enough, sometimes I may make a mistake. But I'm not necessarily getting graded until the end of the semester by you all. You are going to get evaluated as we go through the semester. So try and stick with one or the other. And I should say, if your homework is super well presented, if it's really clear to read the answers, if you answer every part of the question, if it's nice and labeled, if your chemical structures are nice and big and I can see them right away, you're going to get the benefit of the doubt because it's presented right. It looks good. It signals to me that there's a level of professionalism that you're trying to achieve in your work. If it's chicken scratch and if the scan is 45 degrees off, and if I can't read it and it's a really dull pencil or a crayon and you're missing a bunch of parentheses and you're not putting units in, you're not going to get the benefit of the doubt. Even though you might feel like you know what you're doing, make sure that your professionalism shows up on that piece of paper and show me what you can do, because it makes it really easy for me and it convinces me that you're trying to get there. And so sort of presentation of your written work will matter. It won't matter a ton. Canvas is going to be multiple choice. I'm sorry about that. And so if you know exactly what you're doing, you're going to do great on multiple choice, but make your written work neat. It just makes me happy. All right, that's great. That's great. Classes of hydrocarbons, you should know that. Just make sure you study that. I'm going to talk about aliphatic, which is saturated, right? No aromatic bonds or no double bonds or no unsaturated. And so in general, we call these unsaturated. And then we have aromatic. So you'll hear me say aliphatic. You'll hear me say unsaturated. You'll hear me say aromatic. This is what I'm referring to. We've already talked about alkanes and alkynes and things like that. So make sure you remember this. Let's see. I want to do just one more slide. All right. You don't have to click in. You can shout out the answer. How many sigma bonds are in the monomer benzyl acrylate shown below? Count them up. Yell out a number. Great. Anyway, does anyone want to argue 12? Okay. If you look ahead, you know the answer is 22 because of what we just talked about. And I guarantee you that this is on a homework question later on in the semester, and you can't get the right answer unless you do this. And so you get 22 that way. I lied. I'm going to go for one more. It's easy to count pi bonds. Let's see. Which functional group? So this is where we're going to get to right away. Which functional group is not in this molecule? Carboxylic acid. Where's that? Over on the end, right? Alcohol. Where's that? Boom. Amide. Where's that? Oh, I don't know about that. What do we call this? Amine. Where's the ether? Boom. There is no amide in there because amide is nitrogen connected to a carbonyl group. Study that. I'll see you on Friday.